Okay, the next talk will be by Bob MacDowall, and that is Solar Radio Burst Observatories on the Lunar Surface. Let's see.
Okay, hello. We'll look at an item a little closer to home. These are co-authors who are working with my supervisor, Jack Burns, some other people at Goddard Space Flight Center, University of Michigan, and so forth. Anyway, for some time, radio observatory on the lunar surface has been a topic of discussion. Let's briefly talk about the status and plans for one of the simpler targets, which is imaging solar radio bursts. So both solar and other spatial radio missions are typically imaged with ground-based dishes or arrays using aperture synthesis. For instance, the long wavelength array in New Mexico or the long wavelength array at Owens Valley at frequencies greater than 10 megahertz. And that frequency occurs, as most of you know, because the terrestrial ionosphere cuts off all frequencies below 10 megahertz. And so you need to observe below 10 megahertz from space. There has been no imaging to date because you need an array or else a gigantic dish, which you're probably never going to see. There are no arrays of radio astronomy antennas in space, just single spacecraft which have antennas and radio receivers and do observe the solar bursts. So earlier members of the current NESS team, that's NESS here, the Network for Exploration and Space Science, PI Professor Burns. We participated in a concept called the Radio Observatory on the Lunar Surface for Solar Studies, which is such a low-frequency radio telescope and would be operating below 10 megahertz. Actually, it's interesting to note that originally the acronym was the Radio Observatory for Lunar Sortie Science, but when LSS drifted away, the acronym evolved. Anyway, we plan to complete the design for ROLS, although the name and acronym might change, procure and assemble and test the design, and fly it. So there are a number of trades that we will need to work. For example, what will the antennas be? Will we still deposit metal antennas on Kapton and unroll the Kapton on the surface? This is a classic artist's conception of that Kapton on the lunar surface. Such an antenna system would certainly be adequate for solar observations of solar radio bursts, but the beam pattern might not be sufficiently well defined for astrophysical purposes, and so the NESS team is working on the issue of antennas as well as other trades. I just wanted to show you the paper. One of the key paper about ROLS is led by our friend Joseph Lazio and a number of members of the current NESS team. So this complicated diagram here is a bit of detail about solar radio burst science that's of interest. In the background, there is a coronal mass ejection observed by the SOHO spacecraft LASCO instrument. You see the CME, coronal mass ejection, coming out here. A white line has been drawn around it to symbolize the shock that it is driving through the inner heliosphere. And so over the extent of this shock, the geometries with the magnetic field vary from so-called quasi-parallel to quasi-perpendicular. That is the angle between the normal to the shock front and the magnetic field, which is nearly radial close to the sun, as suggested by the orange lines. Anyway, the important aspect of this is that different acceleration mechanisms apply to the different geometries, and the Lunar Radio Observatory would allow us to study this physics. So the question could be, where at the shock does electron acceleration occur? At the Q parallel or the Q perpendicular geometries? And there are other science targets as well. Anyway, let me just briefly discuss those solar radio bursts for you. Over the course of 8 hours of wind, waves, radio receiver data, we have this big guy is a complex type 3 radio burst. It's the Australians who 75 years ago came up with these names. So the type 3s are due to fast electrons typically produced by solar flares. And here's this sporadic, slower drifting emission. This is, again, time and frequency. You can see this is 10 megahertz here, or 10,000 kilohertz. The type 2 burst is produced by electrons that are accelerated at the shock that's moving out through the solar wind. So the point is that different frequencies of the radio bursts come from different distance from the sun. And in this plot on the left, you can see a plot from a paper by Yolande Leblanc et al. Showing as a function of distance where a type 3 burst was occurring as a function of time. It's plotted as frequency and electron density, and our typical relationship between those two things, the plasma frequency, the electron plasma frequency, and the electron density, is this simple relationship. It's not in standard units, but this is the equation that's easy to remember. So anyway, you can see that below 10 megahertz is the bulk of the burst as a function of distance. And if you look at the intersection of these data, you see that 10 megahertz corresponds to 2 solar radii. So the point of this plot is that if you are using ground-based observations, you're studying this little square up here. And you have to go to space to study the bulk of these bursts. And ultimately, you would like to image them. I think our battery is almost gone here. Go. Thank you. So if you want to study those things, yes, sir? Okay.
5 minutes.
Okay, just a couple more slides. If you want to study these things, you need funding and you submit proposals, and so then you are probably asked to have a traceability matrix. Let us briefly just point out that the heliophysics decadal science goals relate to various aspects of solar variability and how it affects the heliosphere, et cetera, and what are the impacts on humanity. And it's true that the radio bursts allow you to ascertain aspects of the electron acceleration, and physically you would like to know what the sources of those bursts are, and you can use those bursts as diagnostics of space weather. So science measurements, instrument requirements, you need to do aperture synthesis from somewhere, and the lunar surface is a good location. You need the appropriate radio receivers and timing systems to collect those data. And the nuisance of the moon is that you have to deal with the thermal environment, and in general in space you have a radiation issue, so your system must deal with those kinds of environmental issues, and you must deploy the things. So this table comes from the Rolls paper of 2011 and shows some of the detailed numbers that are anticipated. You see that we're talking about long wavelengths here, and that controls a lot of what's happening. The angular resolution for the Rolls instrument was not extremely high, because to get that resolution, you have to deploy antennas over a kilometer. And this is obviously something of a challenge, and ultimately you'd like to go bigger than this and perhaps have multiple stations on the moon so that you could have higher angular resolution. The same story does apply for astrophysics, although the advantage is that most of the astrophysical sources don't undergo the scattering that the radio bursts undergo as they leave their source close to the sun. So we would like to go to lower frequencies to see further out into the heliosphere. And we show here from a study at Goddard of Rolls the massive system that they put together for the lunar sortie. Obviously, we will, in the new versions, we will miniaturize, and we will have something that you could deliver with hopefully with a commercial lander or another lander. Also, although I don't have time to discuss it, there are other science aspects, like if you put out a system like this or something similar, you can imagine that in addition to the local dust, there's also interplanetary and interstellar dust striking these rolls of Kapton, which generate electric fields that you detect. So you have a dust detector as well. So in summary, we will review all the info from rolls and similar studies. NES will conduct trade studies to determine what fraction of the generic Lunar Radio Observatory can work for all of the sources. There are some issues that are complex, like if you want to look at the Earth, you have to be on the near side. But if you want to not see RFI from the Earth, you have to be on the far side. So on occasion, the trades are opposed to each other. We will identify the most efficient path with a flexible design that could be implemented as a small pathfinder with a few antennas, or a large station with more antennas. We plan to procure the hardware to build and test a fully functional model to increase the TRL of the low-frequency radio observatory on the lunar surface. And we are working with commercial providers for potential payload delivery on a time frame not too far in the future, but we don't want to go right now because it's solar minimum. We need a few years for the sun to come back. Thank you very much. Any questions or comments? Yes,
Could
sir.
you deploy your antenna with an orbiter in lunar orbit in a similar fashion to large-scale solar what am I thinking? Solar sail, and operate on the lunar far side, to shield Earth emissions. I guess what I'm trying to ask is, why do you need to be on the lunar surface? Isn't the deployment easier if you did that in orbit and you mitigate some of these issues?
Well, the answer is complex, but I'll try to say a few things that are relevant. First of all, it's advantageous to put the antennas down and to know where they are and keep things simple, although obviously there are also issues for the central electronics package of the thermal environment and so forth. To some extent, the system that you're describing is an alternative that is being pursued by others, which is, for instance, CubeSat arrays. If you put up 100 CubeSats or 1,000 CubeSats, you could have a great CubeSat radio observatory. The lifetime of it probably would not be so long, but that's so. In a sense, both are possibilities. There are some other advantages of, well, again, perhaps as you describe, at least part of the time your system could be on the far side of the moon, and that relates, for instance, to the DARE mission, which orbits the moon in order to hide itself from the Earth and the Sun part of the time. So certainly that's a possible solution.
Any other questions? Okay, thank you, Bob.
Yeah, thank you. Thank you, Doug.